Okay, so we're going to continue our work with implicit differentiation, and in particular, let's look at this folium of Descartes. Now, I've presented it here with A as being kind of a parameter. You can play around with that. But we're going to look at it in the case when A equals 1. I want to try and find the equation of the tangent line here at a particular point. I think the point was 1.5 and 1.5. Yeah, right here. Here we go. So we want to find the equation of the tangent line there. Now, unlike what we dealt with when we were able to differentiate implicitly, explicitly, when we differentiate implicitly, I have to give you the x and y coordinate. I don't really expect you to be able to find this for these kinds of crazy types of equations, so I will just give you both x and y coordinates. With that said, let's take a look at differentiating this implicitly. So d by dx, we're going to take the derivative of both sides of the equation. Now, the one thing I suggested is that when you write these things, that wherever you write a y, that you kind of box it off a little bit and try and make sure that you recognize that when you differentiate this, it's more than just 3y squared. You have to differentiate implicitly. Minus 3x, again, times a y, and that's going to equal 0. Now, the first one works out pretty nice. That's just 3x squared. For the second one, when we differentiate this, you've got to use the chain rule. So it's going to be the derivative of the outside times the derivative of the inside. So, Antonio, I know it's early, but maybe you can help me out. What are we going to get when we differentiate that? Perfect. 3y squared dy by dx. So the 3 comes out in front. You still have the y here, and it's, reduce the exponent y squared times the derivative of the inside, which is going to be your dy by dx. Nice. Now, 3 is a constant, so, okay, we can kind of ignore that while we differentiate. We're not going to, get rid of it. We're just going to ignore it. But when we differentiate x times y, what special thing are we going to have to pay attention to? Somebody's thinking said it. Yeah, we have to use a product rule. Even though it looks kind of innocent, it's just x times y, you have to go through the pain of using the product rule. Not much you can do about it. So let's denote one of these as f and one of them as g. So this would be like your f, and that's your g. So it's going to be f prime times g plus g prime times f. Someone want to help me out with f prime? Yeah, it's just going to be a 1 times y plus g prime dy by dx times x. And that's going to equal 0. Nice. Nice. So let's distribute this and clean things up a little bit. We've got 3x squared plus 3y squared dy by dx minus 3y minus 3x dy by dx equals 0. We've got to get dy by dx by itself. At this point, it's just algebra. So let me pause and make sure you're comfortable with our calculating of the derivative so far. So the two tricky parts were here you have to differentiate implicitly with the chain rule. Here we had to differentiate carefully with the product rule. But we're distributing things. And now it's just a matter of getting dy by dx by itself. So a couple of these terms, like the 3y and the 3x squared, those can move to the other side. And it's kind of like a mantra I try and help put into your minds. When it changes sides, it changes signs. All right, so that's going to become a 3y minus a 3x squared on the right-hand side. On the left-hand side, let's be efficient about this. We're going to need to factor out the dy by dx. So it's going to be 3y squared minus 3x times dy by dx. So I'm just factoring out the dy by dx from both of those terms. Moving these two terms to the other side, they change signs like I said. And we get something like that. Almost done. So to finish up here, we can do dy by dx equals 3y minus 3x squared over 3y squared minus 3x. And if you're looking for some simplification, you could actually find some. I could factor out a 3 from the numerator, y minus x squared, and factor out a 3 in the denominator, y squared minus x. We can get rid of the 3's, and that's going to leave me with y minus x squared over y squared minus x. Now, this is going to tell us the slope of the tangent line. But unlike your usual derivatives where we put in a value for x, now we've got to put in a value for x and y. Fortunately for us, that was given. Before I move on to that part, are we okay with where we're at? Thank you, thank you. Thumbs up. Doing good? Is that a yes? Are you okay? Rahana? Yeah. Are you okay with this? Okay, thank you. So we're going to try and find the equation of the tangent line at the point 1.5 and 1.5. And all right, so we're going to plug that in here. 1.5 minus 1.5 squared over 1.5 squared minus 1.5. And the symmetry here tells me that that's going to be -1 for the slope of the tangent line. Let's look at this, and you can calculate that on your calculator and double check me. But let's take a look at it on the graph and see if it at least makes sense. We're trying to find the slope of the tangent line here. Do you expect a positive or negative slope for the tangent line?
Negative.
Yeah, negative. So negative seems to make sense. Let's see if we can't finish finding that equation. This is your x, this is your y, or x1, y1. So it's going to be y minus 1.5 equals -1 times x minus 1.5. So y minus 1.5 equals -x plus 1.5. 1.5 and 1.5 gives me 3. So -x plus 3. Yay. All right. Your last thing that you can do would be to double check that by looking at the graph and see if it fits. It should just kiss the graph at this point, 1.5 and 1.5. Now you're not going to be able to do this on your calculator because your calculator can't graph things unless you're able to solve for y. So more kudos to Desmos that you can handle that, but looks pretty good. Looks good there. We're okay with that one? All right. A few nods. Thank you. Thank you. We're going to skip example E and go down to example D. Now, do a lot of you have your laptops with you? Got Desmos open up that link that I sent you? All right, because I want us to look at this example right here. And in particular, before we start doing any calculations, you can turn on the equations of the tangent line and this point and kind of zoom around a little bit and see where do you think, at what points, the tangent line is going to have either a vertical slope, that is an undefined slope, or a zero slope. So play around with that curve, play around with that slider a little bit, and try and figure out where is it going to have a vertical slope and where is it going to have a horizontal slope. And we'll see how our calculation actually matches what's going on here. So the equation itself is just the equation of a circle. So that equation is x minus 5 squared plus y minus 4 squared equals 9. What's the radius of that circle? Yeah, it's 3, right? It's going to be the square root of this number right here. So if you're asked to find the equation here, it's going to be x minus 5 squared plus y minus 4 squared equals 3 squared. That's our equation. And we can try and find the slope of the tangent line, which is going to tell us where the slope doesn't exist or it's equal to 0. So let's repeat that down here, give myself a little bit more room to play around with things. So I want to find the derivative of this equation. X minus 5 squared plus y minus 4 squared equals 3 squared. And kind of as before, when we differentiate this, gotta put a little bracket around there. Remember that there's a y as part of this. So, Ethan, help me out with the first one. I don't think I want to square this out to differentiate it. Is there a different way I can do this? How can I differentiate that first term?
Just using the special rule, I guess.
The chain rule, yeah. So we use the chain rule. Derivative of the outside would be 2 times x minus 5 to the first power, which I don't need to write, times what? Times the derivative of the inside. What's the derivative of the inside? 1. Nice. Same kind of thing is going to happen with the next one. Christian, help me out here. Derivative of the outside.
Derivative of the outside would be u squared, or it would just be 2.
2. All right, 2 times y minus 4 to the first power, which I'm not going to write the first power, times the derivative of the inside. What's the derivative of the inside this time? Yeah, thank you. dy over dx. And someone for the last part here. What's the derivative of 9? 0. Okay. Solve for dy by dx. I'll give you a moment to do that before I do it up here. Let's see if you can't get dy by dx by itself. Oops, that should be a 10. Yeah, actually, I'll leave it as a 5. Okay. Looking good. Looking good. Actually, the negative is still there. All right. So when we looked at this graph here, well, let's see. There's a few of you got your computer out. That's good. Where'd you find that the place? Where was a horizontal tangent line? What points did it have a horizontal tangent line? Anyone?
8 and 4.
8 and 4 looks like it's a vertical line.
Sorry, 5 and 7 and 5 and 1.
Yeah, 5 and 7 and 5 on. What do both of those things have in common?
5.
Yeah, they both have an x-coordinate of 5. So if I want to know where the slope of the tangent line is 0, so m tan equals 0, that's going to happen where the numerator equals 0, right? So if you have a 0 in the numerator divided by whatever, as long as it's not 0, 0 in the numerator is going to give you a 0 for the slope of the tangent line. Where's the numerator equal 0? What value of x would make this 0?
5.
Yeah, fine. When the numerator equals 0. So when x equals 5. Great. Let's look at things down here and see if we can make a prediction. The slope of the tangent line is going to be undefined when? Yeah, when you're dividing by 0. And that's going to happen when y equals 4. Now on the circle, that happens at two different places. So when the denominator equals 0, which is going to be y equals 4. Thank you. And you can see that graphically. So, bam, here, over here. So when x equals, excuse me, when y equals 4, you've got a vertical tangent there, you got a vertical tangent there. Slope of a vertical line is undefined, so not a big surprise there. But up here and down here, you've got horizontal tangents, and those are both occurring when x equals 5. So very nice. Very nice. All right. Looking good on that one. Let's keep rolling. I'm going to save one for you. So let's try example I, and then we'll come back and cover example G. Let's see. What do I want to do? Actually, you know what? Maybe I want to change up that order. Let me think for just a second here. Let's do an easy one first. I'll let you try it. Example I. I want to find the equation of the tangent line to the point 2, -1, so that's your x and your y, for this equation. So it's just putting into practice what we just did, a couple examples of. So give that a shot. If you're watching this at home later, then you might want to pause the video for a little bit. Try this one yourself and resume when I unpause.
Because that negative is outside of the
All
square.
sides,
And then we plug that into the partial formula.
do I need to do more to find out?
Yeah, the y minus y1. Oh.
And now you're gonna solve for dy by dx. When you get dy by dx, that expression would be just the original. And then when you have dy by dx solved for, then you can put in that to get the equation, the slope of the function.
That's what we're still trying to get a grasp on. Yeah.
Cancel the 3's and throw just a
Go to check.
one out of that.
Yep.
4x plus 12. Function for a number. Squared y dx. Yeah, put a little box in there.
Okay, so let's look at this one and roll through it. So my suggestion on these, when you're differentiating with something other than this variable, then put that other variable in some little box there so you remember to differentiate implicitly. You got to look at it and use the chain rule. You got to differentiate with the outside times the root of the inside. Now here we don't have that problem, because if I were to write this as some kind of outside function, d by dx of, say, x cubed, then the derivative of the outside is going to be my 3x squared, and the derivative of the inside is just going to be dx by dx. So dx by dx is just 1. Whereas when I'm differentiating here, I do the derivative of the outside, I get my 3y squared. The derivative of the inside is dy by dx. It doesn't disappear like it does if I was differentiating with respect to x. Derivative of a constant is 0. I'll move this to the side where it becomes negative. Then divide both sides by this coefficient. Cancel out the 3's. So now we got a nice expression for the derivative. Remember, that tells you the slope of the tangent line right there. I want to know the slope of the tangent line at the point 2, -1. So I'll evaluate this, and that's just my notation here for we're going to plug in the point 2, -1 into the derivative. We get a slope of 4 for the tangent line. When you pull it in here, put it in there to find the equation of the tangent line, you should get -4x plus 7. And I think many of you did. Is that right? Got that one? Holly? Yeah? Okay. Good deal. Good deal. All right. A couple more here to finish up this section. Oh, nuts. Didn't really want to do that. Okay. So one of the things coming your way eventually is going to be the derivative of some more functions. Like in the next section, we're going to differentiate the logarithmic function. But right now, we want to find, say, the derivative of the inverse cosine. So let's think back to the inverse cosine a little bit. We're going to have to derive this for ourselves. We can do that with implicit differentiation. It works out pretty nice. So this is example H. We want to differentiate, well, let's see, we've got y equals a cosine inverse of x. I want to differentiate that relationship. But before I differentiate it, I'm going to rewrite it. What you can do is kind of get rid of this inverse cosine. To get rid of that inverse cosine, which, you know, feels kind of strange at the moment because we're trying to find its derivative, is take the cosine of both sides. Cosine of y, cosine of the cosine inverse of x. What do you suppose is going to happen if I take a function of an inverse function? What happens to these two things here? They cancel out. Perfect. So you get cosine of y equals x. So instead of differentiating this, I'm going to differentiate this. And while I got this here, let's take a look at an associated triangle. I drew one on your sheet there. I'm not writing on the sheet, so let's think. Cosine of y equals x. So if this is my y, cosine was what over what? Cosine is, remember SOHCAHTOA, those kind of things? Good, it's adjacent over hypotenuse. So to put this in the form of adjacent over hypotenuse, I'll think of it as x over 1. Okay, not too bad. So if this is my y, my adjacent side is here, my hypotenuse side is here. What's that leave for this side? How can we find out what that side is? Pythagorean theorem. Let me save you a little bit of trouble here. That's going to be the square root of 1 minus x squared. Okay, so we did a lot of work here. This is just kind of set up for stuff that we have coming. We've got this cosine of y equals x, and I'm going to take the derivative on both sides with respect to x. So d by dx. Now since I'm differentiating some function of y with respect to x, I'm going to put that little box around this. Let's start with the right-hand side. The right-hand side looks pretty nice and easy. What's the derivative on the right-hand side? 1, yay. How about the derivative on the left-hand side? Yeah, nice. Negative sine of y times dy by dx. Okay, great. If I want to solve for sine of y, or excuse me, not sine of y, but dy by dx, it's just a matter of dividing both sides by minus sine of y. Or I can put the minus sign out in front. The unfortunate part is that this is now defined not explicitly, but implicitly, because I've got, you know, y involved here. But let's go back here and put a y in here. Can anyone tell me what the sine of y would equal? SOHCAHTOA. You guys thought you were done with that, didn't you? Ah, sorry. Square root of 1 minus x squared over 1. Or basically just square root of 1 minus x squared, right? That's your derivative. If I had differentiated up here or differentiate down here, I'm still going to get the same thing for dy by dx. That's your derivative of the inverse cosine. So, wow, we derived something. We proved something. Wow. You can go home and tell your friends about it. Post it on Instagram. Pretty nice. What's that? You're not going to get too many likes and views if you post it on it. Hey, look what we did today. All right. Maybe you use your time more productively elsewhere. I'll give you that one. Last but not least, let's look at example G. we're going to do the second derivative. Does anyone remember what the third derivative is called? Jerk function, yes. Well done. Did anyone use that? Anyone yet? Not yet? Waiting for that golden opportunity to call somebody a third derivative? Let's see. So we got example G is going to be x squared plus 6y squared equals 6. And we want to find y double prime. Just some reminders here. So y prime is written equivalently as dy by dx. And this, bless you, this might drive you a little bit batty. This is the proper notation for y double prime in terms of more of a Leibniz kind of notation. It's going to be d squared then y over dx squared. That's the notation we have for this one. Let's start out though by calculating the first derivative as before. We need to pay special attention to this one right here. Okay, so let's apply the differential operator, that is d by dx. We're going to take the derivative of that. The first part should be pretty easy, right? That's just a 2x. How about the second term? What am I going to get there? Yeah, there you go. 12y times dy by dx equals 0. So we'll solve for dy by dx. So that's going to be 12y dy by dx equals negative 2x. Divide both sides by 12y. I get negative 2x over 12y. And we might as well make this as simple as possible. So we'll divide out the 2. And there you go. That's the first derivative. Let's work on calculating the second derivative. I'm trying to think if there's anything clever and tricky we can do here. I'm not seeing anything. So, all right. Let's work on calculating the second derivative then. So again, you're going to take the derivative d by dx of dy by dx equals negative x over 6y. Taking the derivative again, we're going to get d by d squared y. So let me write that over here, d squared y over dx squared. And now I got to differentiate this part here. Okay. What rule am I going to have to use to find the derivative here? Quotient rule. So not too much you can do or say there. You're going to get 6y squared and then a 6y times the derivative of the numerator. 6y times the derivative of the numerator. Derivative of the numerator is just negative 1 minus the numerator, which is negative x, times the derivative of the denominator. Somebody help me out with the derivative of the denominator. Yeah. 6 times the derivative of this, that's just going to be a dy by dx. So, okay. Let's see about cleaning this up a little bit. That's going to equal negative 6y. And then the two negatives are going to be a positive, plus 6x dy by dx over 36y squared. You can factor out a 6 from all of these things and cancel it. I I think I want to take the time to do that, but I'm going to do it in one step. Take the 6 out from the numerator and denominator, and then cancel it. So it's going to leave you with minus y plus x dy by dx over, that'd just be a 6y squared is left in the denominator. And we're getting closer. Unfortunately, you're not going to be able to just leave that dy by dx term there. So what could I do there? Not quite, but I appreciate the attempt. Is there something I can replace dy by dx with? Is there anything at all that is equivalent to dy by dx? Just anything. Just name it. Go ahead. Oh, negative x over 6y. Cool. Yeah. So dy by dx is this. So I can put that in here and continue to keep working on this and clean it up a little bit. Now, for myself, when I give these types of problems on an exam, I'm careful that I don't make the algebra too messy. So that's going to equal negative y plus x times negative x over 6y over 6y squared. I'm going to think of that as negative y over 1 minus x squared over 6y divided by 6y squared. If you had to clean this up, you could. And it's, you know, we're getting past the point that I'm really interested in having you mess with this problem. But if you have somebody in your future that's a little bit more demanding, then to clean this up, you would multiply both the numerator and denominator by the lowest common denominator of all these secondary fractions, is what they're called. Now the denominators here and here are 1. The denominator here is 6y, so that's going to be our default LCD. I'm going to multiply by 6y over 6y. If you simplified 6y over 6y, what would you get? 1. So I'm not changing the value of the fraction. It's just going to look a little bit nicer when it's all done. If I distribute this stuff instead of canceling it, then let's see what I get. In the numerator, I'll have a minus 6y squared. And then here that'll cancel, so it'll be minus x squared. And in the denominator, I'll have 36y cubed. Whew. All right. A little bit ugly there at the finish, but mostly it's just some algebra. The big step there that you should pick up on was this part right here, that you're going to have to replace dy by dx by what we calculated in the first part. All right. Good deal there. Any last comments or thoughts? Something I can clean up for you on this last example G? All right. The end of part 2. Well done.